We're going to continue trying to track down maximums, minimums, and identify intervals of increase and decrease. So what I want to add into the mix today is I want to include it's called a domain restriction. Now what this does is it makes it so you cannot plug in any x you want, right? That way I get a graph that goes forever to the left and forever to the right. In this case, you are restricted, domain restriction, to you can only plug into this equation -8 at the smallest, any number you want in between up to 6. So that means on the graph, it will only exist between those two numbers because that's where you're allowed to start and stop. And because of that, those endpoints, we call them, those can be maximums or minimums. In our previous assignment, the domain was all real numbers, so it just went down forever or went up forever, and the only maximums and minimums occurred when the derivative was 0. So in this one, maximums and minimums will occur when the derivative is 0 and possibly at the endpoints. So let's run through it. Well, I know I need my derivative. So first things first, let me use a different color. Where did I put my purple one? The first derivative is x squared plus 2x minus 15. So again, for the sake of this example, I kind of made it easy to find the zeros. I have to find the zeros, and I'm going to put those zeros on my first derivative number line. So what goes on here? How do I know what to put on there? I have to find the zeros. So if this is 0, if the first derivative is 0, then I'm going to get one at -5 and +3. There are two zeros. Now notice I could only actually go back to -8. If you want, you can kind of show that on your number line. And I can only go up to 6. You don't have to do that, but it might help us while we're trying to think through the problem. Now, I need to know whether it's positive or negative, going up or down, behind the -5, between the 2, and after the 3. And in order to do that, we have to plug in values that are in each of these regions into our first derivative because this is a first derivative number line. That's why I think you should label it so that's clear in your mind. So this is side work. I'll have to erase it. I'm going to plug in -6. So the first derivative of -6 would be 36 minus 12 minus 15, which is 36 minus 27. That is positive. I don't really care what it is. I mean, not that hard to figure it out, but I only care that it's a positive answer. What's going on between -5 and 3? Well, you could pick -4 if you want. If 0's in there, I would do 0 because zeros are so nice. I get 0 plus 0 minus 15. That's negative. And we'll just write it like that. And finally, I need to know what's going on after the 3. So let's plug in 4. You could plug in 5 if you want. So that's going to be 16 plus 8 minus 15. See, I have to know where I'm plugging those in. First derivative. This is all first derivative work. So this is positive for sure. So that is important. On your work, I'm going to want to be seeing that first derivative number line. I want to see the zeros on there and where it's positive or negative. Okay, now what? Well, if I want, I could definitely list my intervals of increase. Now in this case, it starts at -8. And when I check my domain restriction, see how it can actually equal -8? So that's or equals. Up to, but not including -5, because the first derivative is 0 at that -5. It is not 0 at the -8. And that is what? That is increasing. And then between the -5 and the 3, it is decreasing. And after the 3, But stopping at 6, it is increasing. So basically, those always do not get the line underneath. They cannot equal. And the endpoints, these two endpoints, it depends what you see here. If it says it can equal, it can equal. Okay, so I know that I have extrema. I'm going to have one at -8 because it's an endpoint. I'm going to have these that I got from finding where the first derivative was 0. And I'm going to have one here. Maybe I should do those in a different color. That red is not working well. There we go. So these are minimums and maximums, but they occur for a different reason because they're endpoints. These are minimums or maximums, but for a different reason than that, because that is where the first derivative is 0. Both are reasons why a point can be a max or a min. So how can I tell which is which? Well, at -5, look what's happening around it. What happens when you go up and then down? That's got to be a maximum. Up and then down. And this has to be a minimum. Down and then up. Now I'm going to say this, but then we're going to draw it. So maybe you won't be sure how to do that, but let's look. This is the easier one. What's going on at 6? If I'm going up and then down, see, that's a maximum. And then I'm still going down over that whole thing and then up. See, that's a minimum. Well, look, I'm going up the whole time until I hit this spot. Do you see how that's got to be a maximum? It's a high point. All right, now what am I doing back here? Well, it's increasing the whole time, all the way from the -8, right, until it hits that -8. See how it's going up the whole time? Do you see how that's got to be a minimum? So if it helps to overlay this drawing over your number line, do it, right? That helps you think about what you're seeing. Okay, now what we want to do is we want to graph this thing. And in order to graph it, I got to know where these points actually are. And how do you get points? You get them from plugging them in the original equation, not the derivative. That is a big source of error. So I have to plug these numbers into this equation, and I might need a calculator here. So this one is 1/3 times -8 cubed plus -8 squared minus 15 times -8. That's going to be pretty low. So let's see, -8 to the third plus 64 plus 15 times 8. Oh, that's not too bad. This is at -8, 13.33. All right, -5. That's going to be 125, -125 over 3, plus 25, plus 75. That's going to be at -5, 58 1/3. 3 is going to be 9 plus 9 minus 45. So I got 3, -27. And my last one is 1/3 times 6 cubed, 6 squared, minus 15 times 6. So that'll be 216 over 3 plus 36 minus 90. 6, 18. So there's my coordinates. Let's get a look at this thing. Now when you get those large numbers, right, or maybe they're very, like, they're very negative, you don't have to go by scale here, but let's go by tens. 10, 20, 30, 40, 50, 60. Oh, shoot. Sorry, I placed my axis bad. So we got to get back to minus 8. 1, 2, 3, 4, 5, 6, 7, 8. Forward to 6. 1, 2, 3, 4, 5, 6. So the important numbers. $10, $20, $30, $40, $50, $60. And we got to get down to minus 30 about. 10, 20, 30. So when I graph it, I have minus 8, a little bit below the minus 10. I have minus 5, way up at 58.33. And then I have 3, negative 27. And then 6, 18. And I'm not looking for your graph to be a thing of beauty. I'm just looking that it's showing correctly your maxes, your mins, and your intervals. So let's see here. At the minus 8, see how I thought that was a min? It is. Is it the lowest point on the whole curve? No, that is. So that is not an absolute min. That is a relative min. This is a maximum value. Is it the highest point in the whole graph? Yes, so that is an absolute max. This is the lowest point, so that is an absolute min. And this is a high point, but not the high point, so that is a relative max. So this problem is now complete. What do I want you to do on a test or quiz eventually? You have to list these. You have to list all of this, and you're going to need these because I want to see a sketch, which means those points are placed right, but it doesn't have to be a precision graph. I do want to see these points, and I want to see that graph. All right, so now I said we'd do one with a cusp in it because those are weird. So far, I've only done these couple polynomial ones. So let's do that. And it helps to see a few examples because getting the process, there's a lot going on, right? There's specific details, like things you got to remember factually. But then there's like a very important part of this is what do these problems feel like? What do you do first? What do you do next? And repetition is the key there. So let's change our function and let's make it x to the 2/3. And I'm going to restrict the domain like that. Okay, so let's see what the math tells us. I know I have to take a derivative. So the first thing I do, I kind of already made a list. I take a derivative and it would be 2/3 x to the minus 1/3. Now, in my class, I have students learn how to simplify, so we're going to put 2 over 3 cube root x. Now, normally, I would have you rationalize the denominator, but here I want you to stop right there, because that's the easiest form we have to solve for x, right? So we're going to stop it right here. Here is our first derivative. Now, what do we do next? Well, we're supposed to find where this thing equals 0. And we could do some algebra here, but the problems will get more complex, so I want to tell you what you're really looking for. See how this is a fraction? A fraction is 0 when the numerator is 0. Right? When you have 0 over whatever. Who cares? The fraction is 0. A fraction is undefined when the denominator, denom, is 0. So that would be who cares over 0. That is what you're looking for. I don't care how complex the fraction is. There could be a lot going on. A fraction is 0 when the numerator is 0 and the denominator is not. And a fraction is undefined when the denominator is 0. See, so maxes and mins can occur in both scenarios. So you got to check both of them. Now look at that fraction. Can that fraction ever be 0? The answer is no, because there is a 2 up there. There's no x's. You cannot make a 2 into a 0. If it was 2 times x, then I could plug something in for x that made it 0, but that's just a 2. This fraction can never be 0. However, if I plug 0 in for x, that would be 2 over 3 times 0, which would be 2 over 0. So that doesn't equal 0, but it is undefined. So when I plugged x equals 0 in, it made the fraction undefined. So that is, I need that value. So let's make our number line. It's our first derivative number line. And there is only one thing that makes this thing either 0 or undefined, and that is when I plugged 0 in, it made that undefined. So that's the only number that goes on my number line. Now what I have to do is I have to figure out, is that positive or negative, or is that positive or negative? And this is a first derivative number line. So I'm going to plug those into here. How about I plug in, see how there's endpoints? You don't have to do this, but it might help you to remind you that we're only doing that much of the graph. So I'm going to plug in -1 and see what's going on. Well, the cube root of -1 is -1. So that is -2/3. That is negative. And let's plug in +1. That is positive. So I'm going to want to see your number line. From your number line, I can put in my intervals of increase and decrease. From -2 to 0, it is decreasing. And from 0 to 3, it is increasing. And these get the number lines because that was what was given in the domain restriction. Now I see that this is going down and then up. So what I think is going to happen here is at -2 I'm going to have a max. At 0 I'm going to have a min. And at 3 I'm going to have a max. Furthermore, even before I graph it, look at that. That is going to be the low point. I'm sure of that. I do not know which one of these is going to be higher than the other, or if it will be a tie. Possibly, I don't know. So I'm going to hold off on those. All right, so let's try to backtrack. I took the derivative. I found where the derivative was either 0 or undefined. I put that value on a number line, first derivative number line. Then I plugged in a number in here to see if that was positive or negative. Here, a number here, I plugged into the first derivative. Then I started making my lists. The last step is you got to make a graph. In order to make a graph, you got to have some points. This is half the story. How do you get the y coordinate of a graph? You plug an x into the original equation. So this one is going to be f of -2, not the derivative, the original, is -2 to the 2/3. Well, if you know how to do these, this is going to be 4/8, or I'm sorry, it's going to be 8, no, the cube root of 4, positive. Sorry, that was pretty sloppy. But let's punch it in. We got to get decimal anyway. Minus 2 to the, now when you do the 2/3 power, you got to put parenthesis, 2 divided by 3 parenthesis. And I'm getting positive 1.59. When I plug 0 in, that is 0. And when I plug 3 in, 3 to the parenthesis 2 over 3 parenthesis 2.08. So I got everything I need. All I have to do is make my graph, and we have this problem done. I look at how far I got to go. Not too far. So let's see, I have a point at minus 2, about 1.5. I have a point at 0, 0. And I have a point at 3, a little more than 2. Now, if you draw this, I understand because we're just starting this, but this is not a polynomial. This is not a polynomial. Plus, this would be a horizontal tangent line. The slope would be 0. And this was not 0, it was undefined, right? It was undefined there. So the tangent line can't be like this. The tangent line has to be like this. It has to have an undefined slope. The only way that you can make everything work so that there's an undefined slope at 0 and that's a minimum is with a cusp. It would have to go like that and then like that. See? The slope of the tangent line is going down, and then at the 0, see how it's going leveling out this way? It's undefined, just like we figured. And then it's positive after that. So there's my graph. And when I look at it, this one's a little bit higher. So the last remaining piece is this is my absolute, and this is my relative. And I could have told that from there. All right, you better try a few of these. We'll hold up there.